As stars form, we actually find that there's a limit to how much mass they can have. On the high end, we don't find any stars larger than around 300 solar masses. We believe at that scale, as they're collapsing, they're going to get so hot that the pressure gets so high before they begin nuclear fusion that either they will disperse or they will collapse and actually begin fusion, but the fusion rate is going to be so intense that it will have such a high pressure that the outer atmosphere of the star is going to get blown off back out into space, reducing the overall mass. Okay, so we don't really see any stars above around 300 solar masses. Now, the lower limit for a star's mass appears to be around 0.08 solar masses, about 8% of the sun's mass. Now, the reason for this is as the star or the material is collapsing, what would become the core actually stops shrinking due to electron degeneracy pressure before it gets hot enough to begin nuclear fusion. And if there's no fusion, it's not a star. Now, this idea of degeneracy pressure is actually going to come back a couple of times, so it would be something that we should probably understand. Degeneracy pressure is actually a quantum mechanical effect. One of the things that we've learned about the tiny particles like electrons and protons is that no two electrons and no two protons can actually share the same energy level. They have to be unique in some way. Well, as gravity is trying to crush these things closer and closer together, they begin to get so close that they're going to start sharing energy levels, which is not allowed. And so because of that, there's this pressure that is pushing back as we're trying to squeeze the electrons too closely together. Kind of the way that I think about this is like trying to cram too many people into a phone booth. Once you have too many people in there, you're not going to get anybody else in. It's just not going to work. There are too many people too close together, so there's this outward pressure. Okay? Degeneracy pressure is kind of like that. So we know this happens with electrons. We're also going to see it happen with neutrons later on. So because of this degeneracy pressure, the core stops shrinking without getting hot enough to begin nuclear fusion, and because it can't shrink anymore, it's not going to get any hotter. So these things don't actually begin fusion. These objects that have a relatively high mass, almost enough to become a star, these are known as brown dwarfs. The reason why we called them brown dwarfs is originally we thought that they were going to be brownish in color, similar to Jupiter or Saturn in our solar system. But as we've actually discovered them, they're not. There are actually some of these that are magenta in color, which is kind of fun. Now, as we look at the mass distribution of these stars, we find that low mass stars are far more common than high mass stars. And this actually makes sense. If you remember before, we said that high luminosity stars were rare, low luminosity stars are common. It follows the exact same trend. High mass stars are rare, low mass stars are common.